Let's look into what happens after your compensation. So now forget about the right half plane 0. For now you know how to remove it. Now we will go back to the original circuit where you do not have that R in series, and we will see how your transfer function gets modified, or your two poles which are uncompensated gets modified into a compensated pole. So uncompensated poles. So here I am drawing your first stage for the loop gain. So what you had, I called it CO2 and RO2. If you want, you can call it CO1, RO1, but when we started we assumed RO1 and CO1 at the diode connected device, and that is what same thing I am following, so that you do not get confused. GM1, and the second stage is single ended, so I will just draw minus GM3 and this is your CO3 RO3. Let me call it R out, so that we can have everything included there. Okay, and CO3 I can call it C out. Okay. So now omega P1 is appearing at 1 over, and omega P2 is appearing at, so first pole and second pole, 1 over R out C out. Okay, and your gain is DC gain, which is A naught GM1 RO1 sorry RO2 and GM3 R out. So from here you can write the complete transfer function in the form of A naught over 1 plus S over omega P1 into S 1 plus S over omega P2. So this is uncompensated. Now after compensation, let us see what happens after Miller compensation. So I will just copy this. So one way is that you just write the KCL at 2 points, okay, output of each stage, and find the complete transfer function. That is a bit complicated, it will give you a second order equation, you have to find the root and everything. So if I take that way, then probably that requires one complete class, okay. And since we cover that in the undergrad course, so I will just tell you where is it. If after the class you want, you can just look at it. So if you go to our website, okay, in teaching, so this is a second year course, analog systems and lab, and we cover this compensation, but we consider everything, we do not teach them a transistor level design, we teach them everything considering voltage controlled current source. So if you go here you will find the recorded lectures and click here. So, this is what so here I started the Miller effect compensation, finding poles. So, if you click here, so after writing the KCL, this is what we get, the complete transfer function, and you can see there is a right half plane 0, and here you get a second order. Now, you have to find the roots to find the pole. So, you have to basically consider a approximation that you know that after compensation 2 poles will be apart, which means 2 roots of the quadratic equation are much apart. So, in that case you have to approximate this. So, for this if roots x1 and x2 and if x2 is much larger than x1, then ax square, since x2 is much larger, then you can basically for if you want to calculate x1, then what you need to do basically the x1, when you are calculating x1 is much smaller. So, square term of that will go away. So, you will get only linear equation, and from there you can calculate the x. For the second thing, since x2 is much larger, so ax square plus bx will be much larger than c. So, in that case you have to ignore c, and from there you will find the second root. So, that is how you find. So, x1 will become minus c over b and x2 will become minus b over a, and otherwise you can never find the roots of this by using minus b plus minus square root. Using that, it is very difficult, it will take forever to do that. So, from there we calculate, and this is what we find actually, and you can see here this is the Miller effect capacitor Cc multiplied by. So, this was your original pole R01 basically R01 CO1. Now, that is Cc is multiplied by your gain, and that is what effective pole becomes, and these two terms are much smaller compared to this because it is multiplied by gain. So, ignore this. So, your pole location will be 1 over R out multiplied by Cc multiplied by the gain of your second stage, and omega p2 is basically comes this. Okay. So, now I will just tell you intuitively how you can find the omega p1, omega p2 without doing all these things. Okay. So, before I start, I would like to only ask a simple question. What is the, so this is a diode connected device. What is the R out of this? Why 1 by GM? Where does it come from?
Like if we change the voltage by a small amount.
Yeah. So, this is causing a negative feedback because the output is connected back to the input, which is the gate. Now, if I do not have this feedback, what is the output resistance? Not infinite, R out, RDS. So, intrinsic, what is the intrinsic gain? GM R out. Okay. So, if you have this, if I call it R out and you feed it back with the gain A, what is the impedance looking here? R out by 1 plus A. Okay. 1 plus A into GM R out. Correct. Sorry?
R out by 1 plus A into J1 because the loop gain is A into J1.
Yeah, A into GM are out, huh?
1 plus A into
Oh, okay. Sorry. Anyway, forget A. Forget 1. Okay. So, whenever we say 1 plus A, GM are out, we usually write A, GM are out. Okay. So, now you know if you have a feedback, so whatever open loop gain is, your output impedance or resistance will be reduced by that amount. Okay. So, now intrinsic gain is GM are out. So, and so for this case intrinsic gain R out divided by GM R out, that gets cancelled out. Okay. Because you have a feedback, and this feedback is nothing but it is a unity gain feedback. So, if this A becomes 1, you will get 1 over GM. Okay. So, that is what is happening here. Now, take the case here, this particular case, the output stage. So, I have Cc, CO2 and let us say C out. Okay. Can you tell me the impedance looking into this node?
C out plus CC into 1 plus 1 by GM.
So what you have actually, this is equivalent to okay, and what is beta? Cc by Cc plus CO2. So, one way looking into the impedance, if I say that I want to find the GM of this, so how the GM3 will scale? So, the transconductance so if you are looking here, you know that with the unity gain it is a 1 over GM, okay, and if you have an amplifier in the feedback with A, that becomes 1 over A times GM, correct. So, which means your transconductance is amplified. In other word, you can say that R out is scaled down, but GM is increased. So, that causes a GM boosting actually. So, with feedback you, and there are like a lot of circuits we use for GM boosting. Just like impedance boosting you get to increase the gain, you use this for GM boosting. So, now your transconductance will be what? GM3 dash I will call, that will become GM3 into Cc over, correct. So, your compensated so, now you know the impedance looking into this guy is 1 over GM. If I put a cap here, then what will be the pole? GM by C. So, compensated pole at V out, if I call it omega did I call it omega P2 or yeah, omega P2 dash. So, Gm by effective cap at that node. So, you have a Cc over Cc plus CO2 Gm3. What is the effective cap? So, you have a one cap and two caps in the series. So, C out parallel with CO2 so that is coming in series. How will you write this? Let me write this plus. So, in the series how do you write the cap?
CO2 CC by CO2 plus
C C2 CO2
CC by
by
CO2 by CO2 plus
okay, just like a parallel capacitor you write a series, sorry, parallel resistor you write a series cap. Now, if Cc is much larger than CO2, so if Cc is much larger than CO2, then what will happen to the beta factor? That will become 1. So, your transconductance will remain same as Gm3. So, omega P2 dash equal to Gm3 over what will happen to this? So, this is gone Cc, C out plus CO2 plus C out. Okay. So, if you want to intuitively look at, since Cc is much larger, so what would happen by that I mean the frequency at which your second pole will hit, this capacitor will act as almost short. So, when this is shorted, CO2 and C out will come in parallel and that is what you get here. But if that is smaller, then you have to consider this one. So, this is approximation, but if we let us say from your calculation like in the previous case we were looking at 16 picofarad or so, if your output cap is 10 picofarad, then you cannot assume this approximation because they are very close. Then you have to go this complete equation. Compensated what? Omega P1. What will be that? So, what was the original? Original was RO2 CO2, 1 over RO2 CO2. So, 1 over RO2, and what will happen to the CO2? So, you have a two caps there, original CO2 plus gain multiplied by. So, your what is the gain? Gm3 R out Cc, and since this term is much larger, I can ignore CO2, which I can approximate as okay. So, what is happening here? The original pole, now if I draw on S plane, so this is omega P1, omega P1, okay, omega P2, omega P1. I am considering omega P1, the first pole is at a lower frequency, uncompensated. So, what is happening after compensation? You know omega P1 was 1 over RO2 CO2 and omega P2 was 1 over R out C out. correct. So what happened to omega P2 now? GM3 over CO2 plus C out. Will that be at higher frequency or lower frequency compared to the previous one? Higher frequency. Okay, because GM3 will be much larger compared to 1 over R term. What is happening to omega P1? That is multiplied by gain. So C is multiplied by gain. So it will push by the same frequency amount. So if your gain is, let's say, A, then that will become omega P1 over A. So these two poles are uncompensated, or I'll say before compensation. And this is after. So that's what we call pole splitting. So if you remember the previous case, when we didn't have a Miller compensation, the normal dominant pole compensation, where you add the capacitor at the output of your first stage, your second pole is not moving, it remains fixed. But now, I mean, along with your first pole moving at lower frequency, second pole is moving at higher frequency. So now I can push my first pole even at higher frequency because I have a better phase margin. So with the Miller compensation, you can achieve higher bandwidth compared to the dominant pole compensation. So that's the advantage of. So there are two advantages: higher bandwidth and smaller cap, because your cap is multiplied by the gain here.
While calculating the compensated omega P1, we took the resistance to be 1 by GM3 dash. So shouldn't it be in parallel to RF?
Yeah, it will be. When which one you are talking about?
Omega P2 dash. This complete 1 by GM3 dash parallel to RF. Shouldn't be using that.
No, but what is the dominant term here? Dominant term is that will come. So that's why I showed you that if you look at here, there are two terms here, GO2. So that is in the parallel, but since this is a dominant term, so this will go away because GO2 is much smaller, because RO2 is much larger, but GM2 is much larger. So that's why we ignore that. So I am only considering this part, but in reality you will get all these terms. So with the approximation, you usually, that is the if you take only this and this term, and even if you feed all those values, you will see there won't be much difference, because these are non-dominant terms. Okay. So not only GO2, you get this third term also. The GO1, basically the previous stage impedance will get into effect, because that is coupled through CC. Okay, so that makes very complicated, but all those terms are non-dominant, so we ignore them actually. So this approximation, if you take, you will get a correct result actually, whether you take the complete equation or that. The only thing you have to be careful that you cannot always assume that CC is much larger than CO1 or CO2. Okay, until unless you know what exactly the CC is. So sometimes what happens, if you consider one case and the value you get of a CC will be very close to CO1 and CO2, then you have to go back and do your recalculation, everything again.